Hello, stats class. Here is the beginning of our last unit of the year. Believe it or not, one more week of learning stuff. So 14.1a is about multiple linear regression, and you can kind of guess that linear regression means predicting values on a line. Multiple means we are going to have more than one explanatory variable to predict our response. And we're going to use it to predict the value of a response variable which is a quantitative variable. So a lot of what we learned about linear regression is going to still apply. We're actually this year only going to do the two simplest kinds. And then if you take more stats in college, you'll get all of the variations of this. So the two simplest kinds both involve doing one quantitative predictor and one categorical predictor. So we're just going to stick with two explanatory variables for now, one quantitative, one categorical. There's still two types to talk about with that situation, so I'll tell you the second one on Wednesday. But first, we're going to start with the most simple of all, which even then is not as simple as what we've been doing, but that's okay. Here's an example, and I'm going to tell the story as I draw the graph. So give yourself some space to draw kind of a big graph. This goes from January through December. So the date is here, and I'm not going to fill in all the stuff in between. And we're talking about jurors. And so just in case you didn't know, now that you are 18 or almost 18, you can be called by the county or the state to be a juror in a trial anytime they want to. They can just call you and say, come be a juror. And what you're supposed to do is show up and be assigned to a case. But surprisingly or not surprisingly, not everybody actually shows up when they're supposed to come. And so the y-axis thing that we're trying to predict is percent of people who are called who actually show up. And the people running this whole deal, the government, is trying to get this number higher. We're trying to increase the number of people who showed up. And so in 1998, which is when this data comes from, they found that in January, about 50% of the people called showed up. Actually, it would be a little more than 50%. It was, actually, I have the number here somewhere. It was on average about 77% showed up. So actually what I should do is I should put 50% here, and 70, 80, 90, 100% here. Wait, I skipped 60. Oh, that's terrible. 100% is way up there. Alright, so around 77%, which is about like here, of the people who were called in January showed up, but then as the year went by, it went down. And I don't remember how far down it went. I'm just making up some numbers here. I'll get the real numbers in a little bit. But it went down as the year went on, so that towards the end of the year, not very many people were coming, and that's kind of bad. And you could fit a line to this, of course, if you wanted to. And this is the 1998 line. And as you can see, it's kind of sad looking. I mean, it kind of feels like this could have been beginning of the school year, end of the school year, people doing homework. I mean, I've seen this trend other places too. Like in January, people are all gung-ho and they've made their New Year's resolutions and they're willing to do whatever you ask them. And then towards the end of the year, they just don't feel like it. And students do that too. It's kind of funny how that works. But we'll stick with the jurors. So the city or county or whoever it was that was trying to improve this trend said, well, what if we give them some incentives? What if we give them a coupon to something, or I don't know what the incentives were, but in 2000 they decided to try incentives and see what happened. And the values in 2000 were considerably higher than the other values. It was like about almost 20% higher, so that it was nearly 100% at the beginning of 2000, and then it went down from there. I'm purposely making these dots bigger to represent that they are a different data set almost. It's the same basic idea. It still went down as the year went by, but it started higher. So this is the value for 2000 when they did the incentives, whatever those incentives were. And the 1998 was without incentives. And so what we end up with is two lines that describe this data that are approximately parallel. Our first situation that we're going to work with today is parallel regression lines. In other words, the incentives helped about the same amount all year long, and they just raised the whole thing up a little bit. So that's kind of nice. This is the date they were called to be in the jury, and it went down as the year went by. Still, the incentives didn't stop that downward trend, but it did seem to help a little bit. So there's two ways that we can handle this data. The old way, which is what you already know how to do, is we could do two separate regression lines. We could do two separate equations for 2000 and 1998 and just compare them. And so that would be called linear regression, of course. Technically, it would be single linear regression, except we'd be doing it twice. The new way that I'm about to teach you is how to make a single equation for all of this information put together. And I'm going to talk about how to do that. Actually, the first time I learned this, I was kind of fascinated by it. Like, well, why didn't I think of that? It's actually not as hard as you think to think about how this math works, how to make one equation for both sets of data together. So what you do is you have two variables. You have one variable, which I'm going to call x1, it's not a great name for it, that is the date that they are called. Technically, this is by the week, and so it's weeks 1 through 52. As we go through the year, there are 52 weeks. So the date could go anywhere from 1 to 52, and week 1 is the first week of January, and so on. X2 is our indicator variable, which we haven't learned about yet, but we're going to today. X2 represents which of these data sets is it in. Is it in the 2000 data or the 1998 data? It's 2000 versus 1998. So we're going to just have a second variable that tells us which year we're talking about. And that is called an indicator variable. It's categorical, but we're going to make it kind of look like a quantitative so we can plug it into an equation. I can't spell while I'm talking. I'm going to write that all over again. Give it again. It's not indicate, it's indicate. Sorry about that. So it's the indicator variable that indicates which year it is. And so what we're going to do is we're going to decide that one of these is 0 and one of these is 1, just to keep it super simple. We're going to say if it's 2000, we're going to say that's x2 equals 1. And if it's 1998, we're going to say that's x2 equals 0. And that would be incentives or not. And it's very common to use 0 and 1 for this, or if you had 3 categories, you'd use 0, 1, and 2, or whatever you needed to do. You could also, if you wanted to use the actual year numbers, you could use 1998 and 2000. You could use 98 and 100. You could do it however you want. It's a lot simpler if one of them is 0. So I'm going to do that. So I'm going to say one of them is 0, one of them is 1. We don't care about how many years are in between so much. We're just indicating which one we use. Okay, so then we get an equation that looks like y hat. Doesn't this look familiar? Y hat equals b1, or actually no, we're going to stop using a plus bx. We're going to start using b0 plus b1x, and I'll tell you why. It's the first time that our book has done this, and the reason why this is often done because we have two x values. So we have b1x1, and then we have b2 that goes with x2. We have two kind of like slopes, but not really. I'll talk about what they actually mean in a minute. But we have two coefficients of two different x variables. And if I had more, which is something you'll get in advanced stats in college if you keep taking more sets, if I had more variables, I would just keep putting more b's on there. I would have a b3 that went with x3 and a b4 that went with x4, and I could do this as long as I wanted to. We're going to stick with two of them. Isn't that nice of me? Yeah, so this is our predicted y value, which in this case means the predicted percent that show up. And remember that x1 represents which week we're in. x2 represents which year we're in, or more specifically, it represents incentives or not, because that's more important than how many years went by. It's the change that was caused by these incentives or not. And that's our indicator variable. And so this equation could give me a lot of information just all in one equation. And I want to point out, I'm going to do this off to the side because it's not as important, but it is kind of important. Remember that this is based on a sample, and it's representative of a bigger population. So these are estimates of the true equation for the population. And the true equation looks like mu y equals beta 0 plus beta 1 x1 plus beta 2 x2. And that's if I had the whole population. I would use betas instead of b's. These are parameters instead of statistics, but these are parameters that we want to estimate. 3 parameters to estimate instead of just 2. Usually it's just alpha and beta, or A and B. Okay, so let's think about what these numbers would do if I plugged in, specifically I want to think about this incentives or not. What happens if I plug in x2 equals 1 versus x2 equals 0? If I plug in these two values, I could get two separate equations from this. Actually, I'm going to put a big box around this first before I go to this next piece. And I'm going to say this equation could be split up into two separate situations. What happens if x2 is 0? Let's start with that. Let's start with what happens if x2 is 0. That means this piece is gone, and we would just have a linear regression line. No problem. We would end up with y hat equals b0 plus b1 x1. And we already know how to interpret these estimates of these parameters. b0, that's the y-intercept. We've done that before, no problem, except specifically if x2 is 0, that's the no incentives. This is the y-intercept for 1998, which, by the way, is different than the y-intercept for 2000. So let's go back up to our graph, and I'm going to use some highlighters to make this more clear. I'm going to make this one pink. b0 is how high up this y-intercept is on the graph. It's this spot right here is b0. It's my y-intercept for my first group, or my 0 group. Okay, what's b1? b1 is the slope. Well, the slope, we said it was parallel, right? So the slope is actually the same for both groups. This is my slope for both groups. And I think I'll use yellow for that. On the graph, the slope, as you know, is if you go down whatever and over whatever. If you go over 1 week, you go down by b1. It's the estimate of the rise that goes with that run. It ought to be negative because it's going down. So b1 probably is a negative number. And that same slope would work here also. So if I went down and over, this is 1, this is b1, same slope for both data sets. Okay, so that's fine. What if we have this extra x2? What if x2 is 1 instead of 0? That means we have incentives. Okay, then we get an equation that looks like this. Y hat equals b0 plus b1 x1 plus b2 gets multiplied by 1, and you just get b2. So let's do some combining like terms in this equation. b0 and b2 would get added together. And then b1 would be left with the x. b1 is still the slope. x1, I should say. show the slope for both sets of data. Okay, so that's the same as what I had before. Maybe I'll highlight it here also. B0 is the same as what I had before. It's the y-intercept for group 1. But what about B0 plus B2? What is that? Okay, well, this whole thing is my new y-intercept when we add the incentives, or for 2000. In other words, B2, which I think I'll make that be blue, is the extra percent of jurors that we gained by adding incentives. On the graph, it's this piece right here. It's how much that line moved up. B2. And this whole thing from, I don't have a good place to draw this, I'm so sorry. This whole thing from there to there is the new y-intercept. It's the B0 plus B2. I'm sorry that came out messier than it did the last time I did this. But this whole thing is our new y-intercept. So, all of that messiness to say, okay, well, normally what would happen is we would be looking at computer output and it would tell us these three numbers. The B0, B1, and B2 would be in the computer output. So let's look at the actual numbers now. We are not doing inference in this first lesson. We're just doing predictions and maybe a little bit of R squared, you know. So our computer output would have a predictor and a coefficient, and SE, and a T, and a P. And we've seen all of that before. We are not going to worry about the SE and T and P until later. We're mostly going to say there's always a constant, and then there's the date, and then there's the indicator of whether it was 2000 or not, and the computer output says in 2000 for our indicator variable. This is basically x1 and x2, and our y-intercept. This is our actual y-intercept for the first data set. So these numbers are 77.1 and negative 0.717 and 17.8. Those are the numbers spat out by the computer. And I want to point out that we're still looking at this column that says coefficients, and we're using those numbers to find B0 and B1 and B2. They're always in order, 0, 1, 2, same order that's in the equation, which makes me happy. Which, by the way, I can highlight those, and maybe I could. Highlight this, and highlight that. Just to make sure that it's totally clear where I'm getting these numbers from. And B2, which is the third number in the equation, is always the third number in the computer output. That makes me happy. We're going to learn about all of these columns later, probably in 14.1b, right? So I could take this and write my equation. I could say y hash is 77.1 minus, no, I told you it was minus because that's a negative slope, 7.717x1 plus 17.8x2. I just wrote the equation that goes with this, and remember x1 represents the week and x2 represents whether it's incentives or not. We could interpret these things. So some of the stuff we've learned before you might be asked to do again. You will be asked to do again. So interpretations of these numbers, what do they mean? 77.1 is my y-intercept before the incentives. Sorry, I just noticed I missed a parenthesis and it's bothering me. Okay, so before the incentives, this is the percent of the jurors who showed up in January, predicted to show up, because it's an estimate, right? Up in January, without the incentives. So we wouldn't want to assume that it's exactly that, right? It's just predicted. Negative 0.717, what does that number mean? That is the slope. We just talked about that. The slope is the decrease per week, or the predicted decrease per week. I should be specific about that. 17% showing up per week. And the 17.8, what does that mean? That is the extra added on because of the incentives, or we hope it's because, but that's, associated with the incentives. And that's the predicted increase. After the incentives. Now there might be confounding variables, and so I don't really know if it's all because of the incentives or not. If they randomly assign some people to get incentives and some not, then that would be an experiment. They didn't do that. They just offered them to everybody. We could use this equation right here. We could use it to make interpretations. We could use it to make predictions. So if I say it's week 10 and we're using incentives, I could ask you to predict the percent that will show up. And so you would plug in what I gave you. You would take the 77.1 minus the 0.717 times week 10 plus the 17.8 because we have incentives, so we would plug in a 1 there, and that comes out to be 87.73%. So I predict week 10 with incentives would be this much. Without incentives, I would leave that off and just do this piece, and that would be my prediction. They might also ask you to split it up into two equations. We did that with variables up here, but you could also do it with the numbers. So you could split it up into the separate equations for the two different years. So if it's 1998, then I would say if x2 is 0, then I end up with this equation. And I just leave off the rest. It's still x1 though. So I would leave off the 17.8 if x2 is 0, or in 2000, that would be if x2 happens to equal 1, I would include the 17.8. I'll write it out this way first. But then you could also simplify it by combining like terms, and when you add those together, you get 94.9%. That's the y-intercept for the with incentives. That's pretty high. That's my y-intercept for 2000, which remember was the B0 plus the B2. That's B0 and B2 that I just added together to get that. So all that stuff we talked about with the variables, you could also do with the numbers. And then last but not least, they might ask you to do something with R squared. I don't know why exactly, but they always use capital R for multiple regression. I don't know, bigger and better. But if the computer output says R squared is 72%, what does that mean? That means 72% of the variation, we've written this sentence before many times, in the percent of jurors who show up can be explained. Now here's where it's fun. There's two things explaining this, right? By a linear relationship with week of the year and incentives. So we're using two predictors to explain the variation that we're seeing here, and one of them is just how much does it go down per week, and the other one is how much extra can we add on if we're doing incentives. So both of those things contribute to the model and contribute to explaining that variation in the number of jurors. So that's kind of a lot in one day, but that is like chapter 3 on steroids. It's chapter 3 with extra stuff added on because, remember, we're just not talking about two lines that are parallel, and how do you put that all into one equation? And I apologize for these notes being a little bit long. Can't promise the next one won't be, but that's okay. Let's see what we can do.